So what we will do today is, if you remember, last time we started a discussion about crystalline materials. So what we will do today is that we will start talking about the basics of the crystallography. And if you remember, we mentioned that the crystallography is a subsection or subdiscipline of material science that talks specifically about crystalline materials. So we will, I will remind you about what does it specifically mean that the material is crystalline, what we defined last time, and then we will start discussion about Miller indices. So this is the type of indexation and the type of the notation that is used in crystallography to identify certain points, certain directions or planes in crystals. And we will see that this is extremely important because there are certain points in space that can have specific types of symmetries. For example, even if you have a specific type of a crystal, different points in the crystal itself can have very different properties in terms of the symmetry operations that we will define throughout the semester. In other sense, for example, if we talk about directions in crystals, specific directions in crystals can have very different properties. We will learn, for example, that when you mechanically deform a material, the material will likely fail in certain directions and in certain planes than in the others. So it's extremely important that we know how to label these directions, and we will use this labeling extensively throughout the semester. So it's extremely important that you know what we are talking about. And toward the end of the lecture, we will introduce a concept of the reciprocal space. So the reciprocal space is yet another way how we can define symmetry and the properties of the crystals. And it really comes from diffraction experiments. So it's been introduced through understanding the diffraction experiments. Diffraction experiments are the ones that typically give us, and these are the techniques that are most frequently used to understand the structure of the materials. And we will see that we can introduce this alternative way of describing the structure of crystalline materials that help us to understand diffraction, for example. And in terms of the literature, we are following Ellen and Thomas' Structure and Materials, Chapter 3. Specifically, there is a little bit of details there about the Miller indices, and for that reason, I posted a little bit more extensive literature on Stellar, which is the Graf and Henry's book, specifically the chapters that are listed here. So if you do need additional material, it is available on Stellar, and again, Ellen and Thomas is always a good starting point. So last time, we talked about the fact that the crystals have two major components. One is the lattice, and the other is motif, right? So what does it mean? So the lattice, or the net in 2 dimensions, is simply a set of points in space that have the translational symmetry. Right, so these are just coordinates in space, and how they are defined is that there is a specific translational symmetry, and we will talk about this in more details as we go along. Throughout the semester, we will learn that there are only certain types of lattices or nets that can exist in nature that have different types of symmetries. The second component of a crystal, in addition to the lattice itself, is the motif. And the reason why we use this specific illustration is just to illustrate that the motif itself can be anything. The motif itself can have a symmetry, or it doesn't have to have any type of a symmetry. And what we will learn throughout the semester is that the combination of the motifs and lattices is not arbitrary. So if the motif itself has certain symmetry, it can be combined only with a certain type of a lattice. Right? So I can populate this lattice or this set of points in space with only certain types of motifs depending on their mutual symmetries. Okay? And when I populate this lattice or net in 2 dimensions with a motif, eventually I get a crystal. Right? So at the end, the crystalline structure is composed of these 2 components. And initially, we will exclusively talk about the lattices. So we will define the lattice itself, and then as we go throughout the material, we will introduce the motif and the symmetry of the motif, and we will see how these 2 can be combined. So just to let you, to repeat what we learned last time, is that crystals can have different symmetries. They can have rotational symmetry, they can have screw symmetry, etc. And we define a symmetry as an operation that leaves the initial and the final states intact. What that means is that if you have any operation that is a symmetry operation, and if you apply it on a crystal, the initial and the final states cannot be distinguished. And as I mentioned, the crystals can have different types of symmetries, but all of them have translational symmetry, right? So any type of a crystal that you take can have additional symmetries, but all of them do have the translational symmetry. And we mentioned that the translational symmetry simply means that you're translating a crystal to a vector t, and the initial and the final states look identical, right? So an example of a system which has a translational symmetry, is a parking lot, right? And in all of these cases, we assume that the parking lot and that the crystals are infinite, right? So I'm not taking into account the borders or the surface states of a crystal for that matter. So what that means is that, for example, if I'm sitting at this spot of the parking lot, and if I translate myself or the parking lot itself by a vector, which in this particular case is this vector here, my surrounding will look identical. I won't see any difference, right? So I will see the equal number and equal distribution of the parking lots on the left and the right-hand side as before, okay? So I can ask you a question. Does this system, which is a parking lot populated by cars, does it have the translational symmetry? So this would be a net that is populated with objects, right? Does it have translational symmetry? Yes? Only if all of the cars are equal. That's right. So if, for example, I have a white car or a blue car or different shape of a car, right? If I translate by one parking space, my environment won't look identical. But if all of the cars were identical, if, for example, all of them were white of equal shape, then this system would have a translational symmetry, okay? So try to decouple the symmetry of the lattice with the symmetry of an object or motif that populates that lattice and the result symmetry of the system itself, right? So we'll try to make this distinction throughout the semester as we go along. So the question is, what are the most appropriate descriptors that can describe a crystalline system? So we will start with a two-dimensional net or lattice. And we will see that a two-dimensional crystalline lattice can be simply described by two vectors. So one vector is T1, which I will label here. So again, the dots or spots here are individual lattice points. And the shortest distance in this net will be labeled as T1. The second vector will be this T2. So the length of T1, we will call it A, and the length of the vector T2 will be labeled as B, and these will be the lattice constants. Okay? They simply tell us what is the length of these two vectors that define the lattice itself. Then the angle between two of them, which in this particular case happens to be 90 degrees, but it doesn't have to be, will be the next parameter that will tell us, again, what is the angle between these two vectors. So I know the length, and I know the angle between these two vectors, and this completely defines the lattice itself. And how we can, for example, if I have any vector in this particular space, like this T, so T can be written as P times T1 plus Q times T2. So any vector in the two-dimensional space can be written in these terms. But if P and Q are integers, this will define a lattice point, right? So if P and Q are integers, this is a lattice point. So what that means is if I start from an arbitrary position in a crystalline lattice, if I translate that spot by an integer number of the two vectors that I defined as the basis of this lattice, then I will end up in another point in the lattice, okay? So I can define a spot in this lattice that is, for example, here, where the P and Q are not integers. And this is a spot that exists in this two-dimensional structure or two-dimensional space, but it's not a point of a lattice, right? Okay? Okay, so there are also different ways how we can design these vectors and so-called unit cells that are defined by the two vectors. And just because there is an arbitrary way how we can design them, we have to design a set of rules that are typically accepted in crystallography. So, for example, if this was a lattice, in principle, you can design different vectors T1 and T2. And if you translate the space or the parallelogram that is defined by these two vectors, you completely fill out the space. But the choice of these two vectors is not unique, right? So, by definition or by convention, the T1 will be the shortest vector in the lattice itself, and the T2 will be the next in length, where the angle between these two has to be equal or larger than 90 degrees. Okay? And the space or the parallelogram then that is defined by these two vectors is called a unit cell. And the reason why it's called a unit cell is because if I take this parallelogram and shift it by vectors t1 and t2, etc., I can tile the entire space. And tiling simply means cover the entire space. So if I take this parallelogram and shift it by a vector, for example, in this particular case, t2, I'm tiling in this direction. So if I repeat this throughout the space, I can cover the entire space, right? I mentioned that the choice of these two vectors is not unique, and therefore the choice or the definition of a unit cell is not unique. And this will be illustrated on the next slide. So if I, for example, again, take this particular lattice, I just define T1 and T2 as being these two vectors. But I can also define these two vectors as being, for example, T1 is the identical as before. But for example, I define T2 as this one here. And the unit cells are indicated by shaded regions. So for example, what would be the difference between these two? Yes?
The number of atoms they enclose?
The number of atoms that they enclose was the answer. That's 90% correct. There is one particular word that is not correct in this particular definition. Yes?
The number of lattice points it encloses?
The number of the lattice points that it encloses. Yes, that's excellent. So we are talking about the lattice. So the lattice point itself can be populated by atoms, for example, metals, but it can be populated by any type of motif that doesn't have to be an atom. Okay? So this particular unit cell will be called a primitive because it contains one lattice point. And just to convince you that it contains a lattice point, one lattice point, I can simply shift it in this direction. So this is the same unit cell that I'm defining by these two vectors. And you can see that it contains only one lattice point. Okay? So again, for a primitive unit cell, in this particular case, I have two lattice points that approximately have 1/6 of a lattice point, plus two points of the lattice that approximately contain 1/3, and this gives me 1 point. So a primitive unit cell contains only one lattice point. On the other hand, the alternatively defined unit cell is called a non-primitive. And it contains so a non-primitive unit cell can contain any number of lattice points that is not equal than 1, that is larger than 1. Yes?
Where'd you get the 1/6 and 1/3?
Okay, so if you just, for example, look at this lattice point, right? So this lattice point is shared between 4 unit cells, right? So one is just the one that I shaded. One is on the top. The other is here. The fourth is here. So it's shared, right? So roughly, in this particular case, roughly 1/3 of this lattice point is in this unit cell, right? And it's equal for this one, and it's 1/6 for this one, and 1/6 for this one. If you just, I don't know exactly what are the angles in this particular case, but it's roughly that. Okay? Was it your question as well? Maybe I can just illustrate this. It's simpler if you have a very regular. So if the angle was 90 degrees, if this was a lattice point, right, it is shared in between 4 unit cells. So 1/4 will be in this unit cell, 1/4 will be in this one, 1/4 here, and 1/4 here, right? So when I count this unit cell, for example, there are 4 lattice points, each contributing to 1/4, which is 1 total in this unit cell. Because the angle is not 90 degrees in this particular case, right? The angle is roughly 120. Okay, so if you again look at the lattice and the motif itself to get eventually the crystal, again, this is a particular example that I want to show you just to somehow distinguish the two concepts, the lattice and the crystal itself. So if this is a lattice and this is this a primitive or non-primitive unit cell? It's a non-primitive. It contains 2 lattice points. But in this particular case, I can define a primitive unit cell with two vectors T1 and T2. If this is the lattice itself, if this is the resulting crystal, what I'm missing is the motif. What is motif in this case? Again, I'm drawing here the same non-primitive. So what is indicated here with the black lines is the same non-primitive cell that was defined in the lattice of that crystal. So the question is, what is the motif? Yes?
The yellow ball and the red ball.
The yellow ball and the red ball. Again, to emphasize that the lattice itself can be populated with non-trivial objects. They don't necessarily have to be atoms. So in this particular case, it will be a yellow ball and a red ball. Right? So in each point of this lattice, I'm populating this with these two objects together, and this is my motif. So if I draw a primitive unit cell, in this particular case, how many motifs do I have in this primitive unit cell? One. In a primitive cell, we always have one motif, which is again a yellow and a red ball.